Hey everybody, welcome back to Young Engineers of Today. So we're going to do our last Open Rocket class. And this may not take the full hour, and that's okay if that happens. We'll continue with more rocketry stuff on Monday. We'll probably have about a week's worth of material, maybe 2 weeks after that. And then we'll move on to the next topic. But, excuse me, as it stands right now, we've got a little bit more to go in Open Rocket, and then we will be done with it. It's been a fun time, but unfortunately, we gotta move on to other stuff. So let me go ahead and get it open. So the last thing that we need to basically explore with Open Rocket is the flight simulation aspect. That's the last part of it. So we'll spend today going over that, and then we'll break for the weekend after that. That's about it. Eventually it'll open. Maybe. Should be opening. There we go. Must have just double-clicked on it wrong. Oh, there we go. Hey. Okay, so let's go ahead and open up our rocket design. So here's our rocket. Very simple. Nothing really to it. We got our motor, we got our engine block, which keeps our motor or engine or whatever from flying into the rocket and just generally wreaking havoc on the inside of the body tube. We've got our centering rings, which keep the inner tube anchored inside of the body tube. We got our fins for stability, obviously. We've got our launch lug for stability as well. We've got our recovery wadding, which prevents the recovery system from just sort of being vaporized by the ejection charge. However, there is no button for it, so it's shown as a mass component, or it's expressed as a mass component because, like everything else that exists, that humans have created, that is physical, it has a mass to it. On top of that, we've got our recovery system, so we've got our parachute here, presumably attached to the body tube on the inside. We got our shock cord attached to the nose cone and the body tube to prevent the nose cone, to prevent our nose cone from just totally shooting off the top and being lost forever. So we've got a few different components in here. We've also got our motors and configuration, so we've got a whole bunch of different motors here that we can take a look at and sort of get an idea of how high it's going to go and stuff like that. Now these numbers will be slightly different when we run the simulations, but not by a whole lot. It actually does a pretty decent job at adjusting for various factors, and you'll see what I mean later on when I say various factors. So let's go ahead and let's take some time to look at the Flight Simulations tab. Here we've got simulations relating to all of the different configurations we have. So we have A83, B44, C63, C65, C67. These are all of the motor configurations that we created when we set up our rocket initially. Now, I'm going to ask this again, just because one of the best ways to review is to review a concept so many times that you get sick of it. When we're looking at, for instance, A83, what does the A represent? Yeah, the class. How does that stack up to a B class rocket then? Exactly. Less power by 2, half as powerful. Exactly. What about that second, or excuse me, that first number, the 8 in this example? Yeah, you can think of it like the average power. It's referred to as average power, average thrust, something like that, um, which basically refers to how quickly it burns and how much thrust it exerts while it's burning, how much impulse it has while it's burning. So the higher the number, the faster it burns, however, the higher the power. What about that second number? In this case, the 3 that's after the dash. Yeah, the delay time. Um, exactly. It's just the amount of time in seconds that the delay charge burns until the ejection charge blows. That's, well, yeah, but you got them all right, so there you go. So here's the deal. This gives us a little bit of an idea of how, yeah, exactly, uh, how uh, how a rocket's going to perform in flight. Just as a secondary note, I just want to show this. You'll notice that our apogees change pretty significantly among all of these. The empty circle in the center of the rocket? Oh, you mean this one right here? Hold on. Do you mean a thing circled in red, or do you mean the little blue circle next to it? Okay, that represents the recovery wadding. That's just how uh, OpenRocket shows it, because we had to use a regular mass component since there is no recovery wadding button. But since recovery wadding has a mass, we use the mass component button, which is kind of a catch-all for any other thing that they didn't really think of when they put all these components in. And a mass component is always represented as an empty area. And if we look at it in the 3D unfinished, it just sort of has a random kind of textured effect to it. The measurements on the recovery wadding, there you go. Yeah, it gives you some idea of what's going on inside the rocket as well. And let me know when you got those. Usually it's easiest when you're making this mass component. Yeah, +8. Well, you're already beyond the point that that I was going to talk about anyway, so there you go. All right, you got that information down? It's 0.16. However, it's usually easier just to do the mass, the length, and the diameter, and let the computer figure out the approximate density. So you can put 2 grams in for the mass, 3 centimeters in for the length, and 2.3 centimeters in for the diameter, and then it will automatically calculate that one for you. All right, so let's go ahead and head back over to simulations. So now we're looking at all the different motor configurations we have. We got a few things here. We got a whole bunch of statistics, which are empty. We got the name of the simulation, which is helpfully titled 1, 2, 3, 4, and 5, respectively, and we got our configurations here. But we've also got these circles here, which are empty, unlit, whatever you want to refer to them as. This just means we haven't run these simulations yet. What I'm going to do is I'm going to go ahead and click on the first one, and I'm just going to click Run Simulations. There, it turns into a green circle light thing. We get a green check mark next to it. We got some stats. Look at that, velocity off rod, 15.6 meters per second. So that's how fast it's going when it leaves the launch rod, when the launch lug is detached from the launch rod. So, you know, that stat can be important to know because there is a certain minimum velocity required for the fins to actually do their job. I'm not personally sure what those are. I think it largely depends upon the fins, and it's just not information that I have offhand. But that is something that you could keep track of, you know, when you're working with OpenRocket and trying to simulate a rocket that you need in order to get an idea of whether or not the rocket is going fast enough off the launch pad. The apogee is 50.3 meters, which is pretty close to 50.6, and you guys will probably get at least slightly different numbers, and that's okay. That just has to do with weirdnesses when it comes to computers dealing with decimal numbers, because the computers basically have to round when dealing with decimal numbers. They have to approximate because there's no easy way for them to represent decimal numbers. In fact, there are some decimal numbers like 0.11111111111111111 repeating for, you know, forever, that computers cannot represent. They just cannot. And so instead it'll get rounded to like 0.1. No, unfortunately you can't watch them, which is a little bit disappointing. But we can see a cool graph in a moment. But yeah, velocity at deployment, this is how fast the rocket is going when the recovery system deploys. So when the parachute deploys, it's going 2.86 meters a second. that requires a lot of work. That's the only problem. Part of the reason why Kerbal Space Program has spent forever in development is because it takes a lot of work to simulate all the different stuff working together and, you know, doing its thing. The max velocity is 29.2 meters per second, so that's the fastest it goes. Max acceleration is 142 meters a second squared, which is the fastest it accelerates. Yeah, but that's one of the things you do as a programmer is you judge, is you have to make value judgments. You have to go like, okay, will this improve the program significantly, like enough to justify the amount of time it would take to develop this feature? And if you're willing to put in the time and effort and you feel like it's worth it and you know you can do it and you don't really have any constraints like, you know, money or you know, a deadline or anything like that, then, you know, you're more than welcome to. This was a value judgment that they made because a lot of people who are running the software are more interested in at least getting like sort of the hard numbers to figure out, you know, how it's gonna, you know, go. Because when they launch the rocket, like if they're doing this to simulate a rocket that they're building, well, they'll get a visualization of how the rocket works when they launch it, and you know that's pretty awesome. So in this particular stage, really more what they need is a graph showing how it's going to shake out. You know, what's going to happen in the launch with numbers and things like that, so that they can tweak the rocket design accordingly before they actually go to build it. Although, you know, for purposes of launching rockets and stuff like that and watching them go off and, you know, explode wonderfully, I highly recommend Kerbal Space Program. It's a very fun program, especially because it's one of those things where it's like you make your own goals. You know, there is a campaign mode that has goals and stuff like that for you and contracts for you to achieve and things. But by and large, The game is all about making your own goals. You know, like I want to build a space station on the moon. And so you have to figure out how to build a rocket to take all of your space station parts to the moon, and then, you know, rovers to assemble it and things like that, and rockets to take the rovers and all kinds of stuff. And it's pretty neat. But anyway, I'm getting sidetracked here. Time to apogee 3.45 seconds, flight time 15.9 seconds, ground hit velocity 4.41 meters per second. No, don't be sorry. I mean, I'm always happy to like start going off in tangents and talk about things, but I still have to teach you guys the stuff that we're going over as well. So you know, I got to make sure that I stay on track. So that's more like I gotta stay on point. So let's go ahead and plot this. So I'm going to hit plot/export, and I get this window, which just says edit simulation. But it's more than just editing the simulation. What I'm doing is I'm editing the graph. And yes, the reason why you can't read it is because I'm wiggling the window around right now. Not really sure why I was doing that. I felt like it was good emphasis while I was talking. So we got preset plot configurations, vertical motion versus time, which is actually what we're interested in. So we're going to keep it there. But we can do total motion versus time, flight side profile, ground track, stability versus time, drag coefficients versus Mach number, roll characteristics, angle of attack, and orientation versus time. This is stuff that you can check out otherwise, you know. So if you want to make sure that the rocket is stable, you can look at the stability versus time, and you can see that the rocket is not very stable. It just kind of wiggles around all over the place. But, you know, launches are stressful. But what we're interested in is vertical motion versus time. It gives us time on the x-axis, and it gives us altitude, vertical velocity, and vertical acceleration on the y. We've also got flight events over here. We've got motor ignition. Pretty self-explanatory. That's when the motor ignites. It's distinct from launch because you might have multiple motors. So, you know, since we have one motor in our rocket, launch and motor ignition right now are synonymous. But, you know, if you're working with like a multi-stage rocket or something like that, they're not necessarily going to be the same thing, because you're going to have, you know, like a secondary motor that's going to go off as it gets higher into the air. You got liftoff, which is when it actually starts to move upwards off of the launch pad, which is different from launch and motor ignition. Launch rod clearance, again, different from liftoff because the launch rod has a height to it, and so the rocket will travel upwards for a while with the launch lug moving along the launch rod until it clears it. Motor burnout, when this motor runs out of fuel. Ejection charge, when the ejection charge deploys. Apogee, when it reaches its highest point. Recovery device deployment, when the parachute deploys. Ground hit, when it hits the ground. And simulation end, when it stops simulating things. So, you know, there are a whole bunch of different events, but we've really got the most important ones checked by default. So I'm going to go ahead and click plot. And it's going to bring up this nice looking graph. But what exactly is going on here? Well, on this side, we've got altitude and vertical acceleration. On this side, we've got vertical velocity. Right? Yes, we do. Okay, it was covered over by the GoToWebinar window, so I just wanted to double check. And then down on the bottom, we got time. The reason why you've got vertical velocity over here is just so you don't have to be tracking three variables in on the left side of the graph. In addition to that, vertical velocity, as you can see, deals in smaller numbers. So it's kept over here on a different sort of axis in order to keep vertical velocity easy to read. So we've got three lines here too. The blue line is vertical acceleration, the red line is vertical velocity, and, or excuse me, the green line is vertical velocity, and the red line is altitude. So vertical acceleration looks pretty dramatic. Vertical velocity also looks pretty dramatic. Altitude looks pretty calm. But let's break down exactly what's going on here. Yeah, well, part of the problem that altitude is dealing with is it's on the same axis as vertical acceleration. And vertical acceleration goes up to, as you can see over here, about 142, 143 meters per second squared. Whereas the altitude, you know, it's still going 50 meters up, which is almost 200 feet into the air, which is decent, to be sure. It just kind of pales in comparison to how fast the rocket is going, since they're both on the same, or how fast the rocket is accelerating, excuse me, since they're both on the same axis. If we were to compare it with vertical velocity, As you can see, vertical velocity only gets up to 29 meters per second. So if it were on the same graph as altitude, axis and stuff like that as altitude, it would actually look something like that. Like altitude would look, much more impressive compared to vertical velocity. And that's part of the reason why it's put on a separate axis, so you can keep track of it more easily. But let's take a look. So we've got these vertical dotted lines here, and they're labeled. We've got motor ignition, motor burnout, and these are actually solid lines over here. Motor ignition, motor burnout, apogee, and recovery device deployment. These are the things I was talking about. When the motor lights, when the motor runs out of fuel, when the rocket hits its highest point, and when the parachute deploys. So as you can see, the parachute deploys a little bit after it hits its highest point. So let's take a look at vertical acceleration first. Motor ignition. As you can see here, vertical acceleration is about, negative 8.825 meters per second before the motor actually ignites. Why do you think that is? Why do you think our acceleration is negative? And specifically that number, what could be acting on the rocket while it's sitting on the launch pad? Well, what is, let's put it this way, what is constantly acting on the rocket always and forever as long as it's on the planet? Exactly. Oh, sorry, I just said what is constantly acting on the rocket always and forever as long as it's on a planet, which is a bit dramatic, of a dramatic way to put it, but, yeah, exactly. So that's what this is. This is gravity affecting the rocket. Gravity is always going to have a negative acceleration, even if the rocket isn't moving anywhere. It could be moving at 0 meters per second, but it's always going to have that negative acceleration component to it, even when it's sitting on the ground, because gravity's still pulling on it, still trying to pull it downwards. So we're going to have that negative acceleration, and it's going to have that negative component to it. But then ignition happens, so the rocket starts to, the motor starts to burn. As we can see, acceleration starts to go up, dramatically, all the way up to, about 142 meters per second. And velocity climbs pretty precipitously as well. So as you can see, this acceleration gets very dramatic for a moment, and then it levels out to about 25 meters per second squared. And that's just because that's more the average thrust of the rocket. Part of the reason why it looks like less of just a vertical line than it does is because of the amount of data points that the graph grabs. But this is about it's about where the rocket's going to spend most of its time under acceleration. The acceleration that the rocket is going to spend most of its time under, I should say. Words. As you can see, because it's still under acceleration, this is still positive. Our velocity is still going up even at that point, even if it's just like, it looks like it levels a little bit out right here. But yeah, it less precipitously, but it's still going upwards. Then motor burnout happens, and that's when our vertical acceleration drops dramatically. As you can see right here, it's greater than it is here, in the negative direction, I should say. It's more negative than it is here, and it starts to sort of return to that baseline. And why do you think that is? What else acts on a rocket, or really anything that flies? Well, other than gravity. So we got gravity, but that's what the vertical acceleration is returning to over time. Yeah, wind. It's drag. This right here is drag. And as the rocket slows down, drag has less and less of an effect. So as you can see, our vertical acceleration becomes less and less negative over time until it returns to that baseline of just gravity acting on it. So yeah, there's that. And then we've got the rocket begins to slow down. And again, that's just because of our negative acceleration, so it starts to go back down again, but we're still coasting upwards. We're just slowing down as we're going up until a point at which our vertical velocity is 0 and it starts to become negative. That's also, coincidentally, not really, they're in fact extremely related to one another. That's also the point where the rocket hits its highest point and starts to go back downwards again, which is also known as the apogee. So the apogee tends to line up with, it's not perfect on this graph, but it tends to line up with where the rocket hits 0 as far as vertical velocity is concerned and the highest point on altitude. And then the recovery device deploys. So as you can see here, our vertical velocity, again, gets closer to 0 very dramatically because the parachute deploys. And then it slows down the rocket a little bit more until our vertical acceleration is sort of going around 0. So it's not really speeding up or slowing down. Our vertical velocity then equalizes as well. That guy had a what? Oh, it was a cat. You mean what popped up down here? Yeah, it was one of her cats. His name is Bruce, and he's a very nice cat. Anyway, yeah. So that's that sort of stabilizes. We still have a negative vertical velocity though, so obviously the altitude decreases steadily until we hit the ground, at which point you got the ground hit event, which again is not going to be perfect. As you can see, it happens a little bit after altitude is like has hit 0 and it passes it a little bit, and then it goes, oh, I hit the ground, okay. But yeah, more or less, that's the idea. And there you go. That is what one of these simulations looks like over time. So let's take a look at some of these other ones and see how they stack up. So run this one. Again, velocity off-rod, 18.2, apogee, 134. Now we're looking at more than double the height for the apogee. Velocity at deployment is going a little bit faster at deployment. Excuse me. Optimum delay. I didn't point this one out before, but optimum delay is roughly the time between last motor burnout and maximum possible altitude. So this gives you a hint as to what you should set your final number for on your motor configuration. So B44 is pretty close to our optimum delay. It deploys a little bit early, but it's not too bad. A83, we deploy a little bit after optimum delay. So that's after the rocket reaches apogee and starts to go back down again. So as you can see, we're still accelerating upwards, or we're still moving upwards a little bit because our recovery system deploys a little bit before optimum delay, and it's going a little bit faster. Max velocity is 53 meters a second. Max acceleration 180 meters a second squared. Time to apogee 5.25 seconds. So as you can see, even though this is a B44, this rocket is still going upwards when the recovery system deploys. It spends a total of almost 38 seconds in the air and it hits the ground at almost 4 meters a second. So let's go ahead and plot that. Boop. So as you can see here, the recovery device deployment happens a little bit before the apogee. So the parachute deploys first, which explains why we get this massive downward dip in vertical acceleration before it equalizes again and goes back to around 0 and oscillates between the two, which this right here is just sort of an artifact of the simulation, because really you can see where the simulation takes data points, because the way it works is it gets sort of a snapshot of change in time, and as that snapshot is about half a second long, it looks like. So if the acceleration is not 0 and the parachute is deployed, it's going to try and head towards 0. However, it hits 0 at some point between when it last took a snapshot and when it's taking the current snapshot. So then it sees, oh, wow, okay, it's 0, or it's not 0. It should move towards 0 again. And so it goes back in the other direction, and then back, 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 and then back. Anyway, that's just because the computer only takes so many pulls of the rocket state per simulated second. Anyway, big acceleration equalizes like it did before. Motor burnout, big deceleration equalizes because of drag, or big deceleration because of drag equalizes as the rocket slows down. Big deceleration because of parachute equalizes because of parachute. And, you know, the velocity stays pretty even, and the apogee stays pretty consistent as well. So by and large, this is pretty okay. You know, I mean, we're losing maybe a little bit of apogee, who knows? But by and large, this is pretty all right. However, this isn't always the case. Let's go ahead and run C63. So velocity off rod, 17.5 meters per second. Apogee, 276 meters. Velocity at deployment, 31 meters per second. This is widely different from the 3.46 and the 2.86 we had before. This is, well, actually, I was just about to get there. Excellent question, though. So this is what I was about to say. So yeah, 31 meters per second, we've got a red exclamation mark here. If we mouse over this, it says warnings, recovery device deployment at high speed, 30.9 meters a second. That is really fast. In fact, that is about a tenth the speed of sound. That parachute deploys at about a tenth the speed of sound. Yep, and that's why that's there, is because that parachute deploys when the rocket is still moving really quickly. So let's go ahead and take a look at this plot. Now, that doesn't look right. Now, here's the confusing thing. Yeah, for some reason that I don't entirely understand, on this particular plot, and it did this in my last class too, yeah, it switches the colors for vertical acceleration and vertical velocity. So vertical acceleration in this graph is green, and vertical velocity in this graph is blue. But this still looks very wrong compared to what we had before. Like right here, vertical velocity, look at that, just get entirely destroyed. And that's because the parachute deploys. So it's going 31 meters a second roughly, parachute deploys, and then suddenly it's going 0 and then negative, and then, you know, it equalizes. But that's bad. You know, speeds like that, we're talking about ripping the parachute out of the body tube. That's bad. However, that's nothing compared to what's going on here. Look at that. That is our vertical acceleration. So it goes ignition like before. We get up to, you know, almost 200 meters a second, maximum acceleration, 200 meters a second squared. Then it goes down. Then it levels out. Then it goes down again at motor burnout, and we get drag, which sort of starts to return to gravity, and then the parachute deploys. So just for funsies, what are we looking at here? What is this negative acceleration? 542.5750 meters per second downwards. So I already did the math in my last class. That is roughly equivalent to Mach 1.5. For an instant, for a moment in time, this rocket experiences deceleration or downwards acceleration at a rate of Mach 1.5 per second per second. If it kept this acceleration, it'd be going Mach 3 after 2 seconds. That's a pretty dramatic deceleration. And that's why there is a serious concern that this parachute's going to get ripped out of the body tube. Yeah. Z-class with a crazy parachute. Anyway, this is to be fair, this is the kind of deceleration that can be experienced on full-size rockets. Still not ideal. You don't really, want to be undergoing that kind of acceleration all the time, but re-entering the atmosphere and stuff like that, it can happen. But yeah, that's those sorts of accelerations can be experienced by full-size rockets, but it's not really ideal for them either. That's just something that engineers have to work around and deal with, and try and minimize. This is something that we don't want to have happen to the rocket. We haven't built our rocket out of aluminum and steel and titanium and all this stuff, and we don't have all kinds of secondary and tertiary systems on the inside in case one of them fails because of stress. We built it out of cardboard and paper and plastic. This thing's going to fall apart the minute that happens. So the lesson to take away from this is that 3 is far too short a time for the delay charge until this rocket deploys its recovery system. Let's try 5. Run that simulation. Hey, look at that, check mark. Boop. We don't have that exclamation mark anymore. As you can see here, 8.85 meters a second is a lot more reasonable. Still a little bit high for maybe what we want, maybe, but excuse me, it's a lot more reasonable for what we need. Our max velocity is 94.2, our optimum delay 5.82, so we're getting closer as well to our optimum delay. On top of that, our apogee is 40 meters higher. So now that we've given our rocket ample opportunity to continue coasting upwards, we gain an additional 40 meters, an additional 160 feet almost, like 150 feet in altitude. Flight time, 82.7 seconds. So we add an additional 10 seconds to our flight time as well because we, don't cut off the apogee. It hits the ground a little bit faster, but, oh well. Let's take a look at that plot. This is much more reasonable. Again, we still have this pretty dramatic deceleration going on here because it recovers just a little bit before apogee, and it's still going pretty dang fast, so you can see it drop off right there. And again, our vertical velocity has returned back to green, and our vertical acceleration has returned back to blue. And it's still a more dramatic deceleration than our motor burnout, so it's not exactly the perfect place. It's not exactly the perfect time for our recovery system to deploy, but this looks a lot better and a lot saner than our last launch. So let's take a look at the last one then. Boop. Run simulation. Plot. That looks much better. Taking a look at the numbers, well, it shouldn't look better. I think that's just a trick of the mind because it's actually going faster at deployment time. So if we made this like a C6-6, we'd probably see much closer to an ideal velocity. But anyway, apogee gets a little bit higher, so we allow it to reach its full apogee before before we deploy the recovery system. It hits the ground a little bit faster. It flies for just a wee bit longer, just a wee bit. And as you can see, our optimum delay gets a little bit longer, which is strange. But a lot of that has to do with the fact that it actually, because it reaches its apogee naturally before the recovery device deploys, we get a clearer picture. This, it's basing its optimum delay off of the apogee here. Or not. That's weird. Well, okay, again, we'll just chalk that up to weirdnesses with floating points on the computer. But otherwise, everything looks okay. So, just to get an idea, based on this, you can sort of get an idea of what we should be running, probably, for a motor. So let's go ahead and change this to a C6-6. And let's see how that looks. Now, obviously, all of our simulations are out of date because it assumes that all of them have been changed. It doesn't really keep track necessarily of, each individual one. But we'll compare this to simulation 4 since that's a close, comparator. 314 meter apogee, perfect. Look at that velocity at deployment, 2.97 meters per second. That's beautiful. That is beautiful. That is a nice, gentle deployment time for the parachute. 5.97 seconds. Look at that. We're right on the money with our configuration. 188 meters a second. Time to apogee, 7.74. Flight time, we add an entire second onto our flight time after letting it reach apogee and then, do all the deceleration and everything like that. Ground hit velocity is always a little bit faster when the rocket deploys the recovery system after it hits apogee. And that's just kind of how it is. When it deploys the recovery system before apogee in this system, it always hits the ground slower. But, I feel like that's a reasonable trade-off considering that velocity at deployment is just beautiful. So, here's the fun thing. This is just as a side note because this is pretty much everything you need to know at this point about OpenRocket. But here's the fun side thing. Remember how I was saying before about how it doesn't care what engine you have slotted in it? It doesn't try and make sure it makes physical sense. So let's go ahead and put a G80-7 in there and run a simulation. That doesn't look great. It's going 39.1 meters a second when the recovery system deploys. Let's take a look at that plot. Oh, baby. Look at that flight time. Almost 270 seconds. It is in the air from launch until touchdown. That is over 2 minutes. Or, excuse me, 4 minutes. I can math. It's over 4 minutes. That thing spends 4 minutes just flying through the air. But look at this deceleration right here. Look at that deceleration. Now we're talking like Mach 2.25. Yeah. Well, yeah, it's jury's out on that one. Not sure I can grammar all the time. Mach 2.25. In fact, it experiences that deceleration because of drag. Almost. It experiences about Mach 2 in deceleration because of drag. Nice. But on the flip side, oh wait, why is that max velocity? Oh, because this is strictly altitude. Whoops. Over here. Okay. Um, so I take that back. It experiences at about Mach 1 in deceleration and Mach 1.25 in deceleration when the recovery system blows. It's going about Mach 1.5 at maximum speed. So it's a really fast rocket. It's really fast. It gets up to 1,500 meters at apogee before the recovery system blows. So like let's see here. Optimum delay 10.7 seconds. Let's go ahead and change this baby to a G8011. See what happens. Run simulation. We still have an exclamation mark. But here's the reason why this one has an exclamation mark. Body calculations may not be entirely accurate at supersonic speeds. That's because things get wonky when you go into supersonic speeds, because air behaves differently when you're going at supersonic speeds. Let's just take a look at this for a moment. There is a strange thing. Oh, come on. There is a strange thing that happens over in this neck of the woods. Right. Well, first off, there's this. It experiences acceleration until the rocket actually starts to lift off the ground, and then, again, it hits maximum acceleration. Now, something happens before motor burnout, and that is our vertical velocity slows down pretty considerably, but our vertical acceleration slows down before that. Now, what do you think is happening in this particular area, like right around this little notch right here? Why do you think this just suddenly gets all kind of wonky? No, the parachute actually doesn't happen until much, much later at this point. However, there is a very specific speed that this is going. It's actually right about here. There's a very specific speed that this is going. It has to do with the wind. Think about how fast this rocket is going at this point. Basically, it's breaking the sound barrier. So there's a whole bunch of air that's built up in front of it. That's actually breaking the sound barrier right about here. There's a whole bunch of air that's built up in front of it. There's this air pocket that's built up in front of it, and kind of finally goes pack or boom, because a lot of times that's why it's called a sonic boom, is because it's pretty dramatic and loud, and it makes things shake, and it makes your rib cage rattle, and you feel like the wind gets knocked out of you if you're close enough. There is a large boom that happens there, and suddenly that pocket of air just goes boom, and then it moves past it. It doesn't exactly move past it. It's not like you can move past the air because it's not really physically possible. All that air buildup suddenly just releases. There's a vacuum, and air rushes in to fill it, and that's where you get the boom noise from. As a little side note, that's why guns tend to be loud. It's not necessarily because, I mean, there's definitely the sound of the propellant igniting and blowing, but a big part of the reason why guns can be very loud is because it is the boom from the bullet reaching supersonic speeds, breaking the sound barrier. Anyway, that's just a little aside. But on that note, I'm going to go ahead and say that you guys have pretty much learned everything you can about OpenRocket. If you're interested, I challenge you to continue. See if you can build a rocket that can get as close to 220 meters in height as you possibly can without going over. The reason you don't want to go over is because that's when you need to start getting in contact with the FAA and letting them know what you're doing. So if you can get as close to 2,200 meters in height as you can, 2,200 meters in height. As you can see, this gets up to 1559, so you can do better. And this doesn't even make physical sense. So the rocket also has to make physical sense. Get as close to 2,200 meters as you possibly can without going over. Ideally, without even really reaching it. If you can get to like 2199.9, and you know, awesome. I unfortunately don't really have like a reward to give you or anything like that. This is more just for your own personal enjoyment and give you something to sort of experiment with all the different configurations and features and get yourself more comfortable with OpenRocket. But, you know, I invite you to do it if you're interested in it, and let me know on Monday how that goes, or whenever, you know, whenever you finally nail down that rocket. But with that, yeah, we're going to go ahead and call it a class. So I'm going to do the poll questions, and I'm going to drink some water while it's happening because my throat is killing me. And then we'll leave it open to question and answer time. And if you have any questions about anything, you're more than welcome to ask them. They can be related to the material or not, obviously. Otherwise, you're more than welcome to head out and have a wonderful weekend, and we will see you on Monday.